All right. So I've got 405. I'm going to get started here. This is COMP2804, Discrete Structures 2, and I'm Daryl Hill, the instructor. So just to start, I'm going to address a question from somebody had on assignment 2 in the chat. They asked for question 7, where we developed this sort of recursive definition of the number of ways that we can tile this, what did we call it? This board. They asked if A and B were related. So A is the base cases and B is the recursive algorithm. So you need both to have a well-defined recurrence, right? So for example, the Fibonacci sequence, we had base cases of F0 equals 0, F1 equals 1, and F4. And then for n at least 2, we have f of n equals f of n minus 1 plus f of n minus 2. So this would be equivalent to what you're going to find in part B, and this would be equivalent to what you're going to find in part A, and you need both in order to have a well-defined recurrence, right? So by well-defined, I mean I give you a value of n, and you can tell me, I mean, you might have to go through and calculate it all, but it does have a value. If I'm missing the base cases, or if I give different base cases, these will have different values, right? So right now, the Fibonacci sequence is 0, 1, 2, or sorry, 0, 1, 1, 2. But let's say I did, what can I say here? I'll take 4 here and 7 here. Well, then I get a different sequence, right? I have this same recursive definition, but the values for some particular n will be different. For instance, F2 would be 11. So F2 here is 1, but using these base cases, I get 11. So you need both in order to have a well-defined sequence or, recursion. So you're going to determine them separately, but then together you will use them to prove this, basically. All right, so I think that answers that, unless does anybody want clarification? Okay. All right, so we're here today on February 7th. So the test was, so I gave the Scantrons to the Scantron people, and they said by Friday. Often they're done before that, but there was an awful lot of them. There's about 500. And this test and the test written in the other section were the same because I accidentally submitted the same file for both. So that was my blunder. And I tried to keep it a secret as much as possible, but when I gave you guys the test, of course, you had section B written on it. That was why. So yeah, when you look at the solutions on Brightspace, it's the part B, right? And yeah, I don't think anybody from section B realized it, so I don't think they had an unfair advantage. We'll see when the statistics come out, I guess, but all right. Okay, so assignment 1 has been submitted. Assignment 2 is out, of course. I added a bonus question at the end. It's based on Euclid's algorithm. Shouldn't be too hard. Don't make it harder than it is. You can reference, it's called Slowclid, and it's an algorithm, and you can reference the Euclid, which we're going to take up today. And if you draw parallels, you can solve most of it without doing all the calculations. All right, so. All right. Any questions before we get started? Okay. All right, so today we're going to talk about recursive algorithms. Last class, we talked about recursive functions, and we looked at the Fibonacci sequence. Right. And then we drew parallels between the Fibonacci sequence and other, sorry. Yeah. All right, well, tried. Between the Fibonacci sequence and other things that we're trying to count. So we have a closed form for the Fibonacci sequence, so we can map things directly to it it's sort of useful since we already understand it. But there's lots of other recursive functions that have a similar form. But today we're going to start talking about something that's closer to what we do in computer science, which is recursive algorithms. So they're kind of neat because you can solve a problem without actually knowing how to solve it, as long as you know the base case and how to sort of use the magic of recursion to solve it inductively. But then, of course, once we solve it, we have to analyze it, which was where the counting comes in. So we're going to look at a message problem. In the textbook, it's called the gossip problem. So we're going to write and then analyze a recursive algorithm to solve a particular problem. And this particular problem is if we have, at least 4 people, and each person has a message, right? So each person PI has a message MI, and they want to transmit that message to everyone else in the network. So at the beginning, everybody knows their own message. So P1 knows message 1, P2 knows message 2, all the way to Pn. And then at the end of our algorithm, what we want is that everybody knows every message. Okay, and so how does somebody learn about messages that they don't know about? Well, we'll say that they connect over the network, and 2 people can connect at a time. And when they connect, they're going to share all of the messages, right? So if I have a person PI and they connect to PJ, then PI will learn all of PJ's messages, and also PJ will learn all of PI's messages. So we're going to share everything that we know. And then in the end, we want everybody to know, everybody in the network to know everything. All right. So, and the constraint, well, what we want is to get from table 1 essentially to table 2. And we want to use the fewest connections possible. So we want, like a phone call, for instance, if I don't know who makes phone calls these days, but if I call, well, and you can also do 3-way calling in real life, but here we're just saying every connection is between 2 people or 2 terminals or what have you. All right, so we want the fewest number of those in order to spread the messages everywhere. Okay, so questions on the problem we're trying to solve? Okay. All right, so our first stab at designing an algorithm, of course, brute force. I mean, it's not going to be the most efficient thing, but it can help us understand the problem. What we can do is have everyone message everyone else, right? So everybody connects to everybody. So every time I have a connection, I'm choosing 2 people out of the n available. So that is n choose 2 connections in total, right? And then if I expand that out, it's equal to n times n minus 1 over 2. So this is brute force. This means, it's probably overkill. So let's see if we can do a little bit better. Let's try a smaller version of the problem. So let's start with 4 people. Each person has their own message. And at the end of it, we want everyone to have all 4 messages. Okay, so we will just take the following sequence of actions. I start with this. And then the first connection I have is P1 connects to P2. So now P1 knows both of P1's message and also P2's message. And P2 also knows both messages. At which point I can say, well, I'll take P3 and connect to P4. I'm not doing anything particularly clever here, but I'm just going to see, trying it out if I can get away with fewer messages. So once P3 and P4 connect, then P3 knows both message 3 and message 4, and so does P4. And now I have basically these guys that know one half and these guys that know the other half. So I need to communicate between these people. So P1 connects to P3. Now I have P1 and P3 who know every message. And now I can also do P2 connecting to P4. And then P2 and P4 now know every message. Okay, so I had 1, 2, 3, 4 connections. in order to solve this problem with 4 people. Okay, so, and that's possibly optimal. We're not going to prove that at this time. It is optimal, but we're not going to prove that at this time. What we do notice is that if I use brute force, that is, everybody messages everyone else, then I would have 6 total messages, right? So 4 choose 2 is 6. So here it took 4, so I did a little bit better. Okay, so the question is, I guess, this is on order of, n choose 2 is on order of, order of n squared. And what I want to do is I want to solve this problem using a linear number of messages. So I want some order of n, maybe some constant, some lower order terms, but it's going to be a lot faster than n squared. All right. Questions so far? All right. All right. So what we did right now, we solved it for 4 people, and that's going to form the base case of our algorithm. So when I do a recursive algorithm, when I design one, I need a couple things. I need to be able to solve it for the base case. So I need to be able to solve it in the simplest instance of it. And then the other thing I need to do, similar to when we did induction or when we've done induction, is that if I have a solution, if I know I can solve it for less than n people, then can I use that solution to solve it for n people? So we need an algorithm that uses a smaller recursive call. I assume that that recursive call works, and then I use that in my solution. So that's the design of this algorithm. So we're going to solve for n people by assuming that we can solve it recursively for n minus 1 people, and then use that in the main one. And this is, again, similar to induction. It's our inductive hypothesis in some sense. And it's reasonable because I have a base case. So I have a spot where sort of, the buck stops here, I guess. So, all right, so here's our problem at the start. In general, I have n people. Each person has 1 message that they know. And I want it, at the end, I want everybody to know every message. So my first step, what I'm going to do is I'm going to have the last 2 people connect. So they're going to share this message. And we'll talk about in a second why we did that. But of course, the result is that person n minus 1 knows message n minus 1 and message n. And so does person n. This part is not so important, but this part is. Because when I recursively solve it, I'm going to assume that I can now solve it for this. But when I solve it, I'm going to have not only message n minus 1 spread all over everyone, but also message n, right? Because everybody pn minus 1 talks to is going to share this message, but also this message. So I can sort of bundle them together as one message now. So when I recursively solve this, I'm not just spreading message m1 to m minus 1 among the first n minus 1 people, but I also include up to mn. All right, so this first call makes sure that this recursive call solves the problem for the first n minus 1 people. Okay, so yeah. Since I can recursively solve it for people p1 through pn minus 1, then now everybody from person 1 to n minus 1 knows every message. And the only person left is person n that doesn't know all the messages. At which point person n can talk to anybody. But we'll have them talk to pn minus 1 again. And now everybody knows all the messages. Okay. So that's the algorithm at a high level, and how I solved it. I had a base case I solved it in the simplest case for 4 people. And then I assumed I could solve it for a smaller case. And then I used that assumption to solve it for the larger case. And that's, and how did it happen? I don't know. Magic. Yeah. Questions on that? All right. Yes. So written down in pseudocode, our algorithm would look something like this. This would be the base case, right? So these are the 4 calls that solve it for 4 people. Otherwise, I'm going to make a recursive call. Well, first I'm going to have pn-1 message pn. I'm going to make a recursive call that solves it for the first n-1 people. And then I'm going to make this call again. All right, so, and we've proven that that works using sort of an informal induction, right? We didn't officially write down the induction, but assuming that we solved it for the recursive case, we solved it for the full case. So that's fine. So now we want to analyze the runtime of this. So first we're going to write it as a recursive function. So like any recursive function, we need a base case. So what we're going to say is that C, the function C, represents the number of messages that I send for, in this case, 4 people. So C of n is number of messages or connections for n people. Okay, so C of 4 is 4. We know that because we solved it explicitly, and also it's right here. And then using this, we can, derive a recurrence. So if I didn't have n equal to 4, if I had some other value of n, then we execute this part. I send 1 explicit message, 2 explicit messages, so that's here. And my recursive call on n-1, I represent using this, the C function again. Okay, so I can derive a recurrence quite easily. I have my base case and my recursive case. Pretty simple in this case. All right, so that's, now we're in a situation that we solved before. We have a recursive function, a base case, a recursive case. We want to plug some values in and see if we can spot the pattern. Once we spot the pattern, we get the closed form, and then we prove it using induction. Okay, so C of 4 is equal to 4. If I take C5, well, that's equal to 2 plus C4, which is 4. So 2 plus 4 is 6. All right, I'm skipping I'm plugging the values directly in here, but this is basically C5 equal to 2 plus C4. And then C6 is equal to 2 plus C5. Well, C5 is 6, so I plug that in down here. So this is equal to 8. C7 is equal to 2 plus C6, which is 8, and that becomes 10. And so the pattern seems to be, I'm going to increase by 2 every time. And if I do a little bit of magic and look at the base cases, I can come up with this guess. C of n is equal to 2n minus 4. There's other ways to write that, of course, but this seems to be the easiest. All right. Questions? Everybody following? Yep. I just looked at the algorithm. So basically, this is the base case here is directly here. So I'm just counting the number of times I call this message function or whatever. And then this directly maps to here. So this is 1 message. This is the second message. So I have 2 here, and then this is the recursive call. Yep. Other questions? Yeah. Yeah, that's there is an exercise which I can go over later, maybe. Actually, I have to look at the exercise. So I got, this is yeah. I don't think it extracts well if you use less than 4 people. It's just sort of an artifact of the type of algorithm. But yeah, I'd have to get back to you with that, actually. Yeah. Yeah.
Like in at the start of the problem, you say it has to be more than 4 people.
Yeah.
Or at least.
Yeah, but I think it's there's a certain amount of symmetry that happens at 4 that you don't really get in the if you use earlier base cases, right? So if we, for instance, tried to solve it for 3, P1 messages, or P1 and P2 message, and then P3 messages, any of these, and then P2. Yeah, I guess I could do it at 3, but that's a really good question. I do want to answer that, but I don't have the answer right now. Yeah. Anyway, I would love to sit here and think about it, but any other questions that I promise to answer later? Yeah.
Clarifying that it was the beginning, right? So those 2 methods between P and minus 4 to P event. The first initial one,
yeah. So yes, this 2 here is this plus this. Is that your, yeah? Okay, yeah. And then this is if I did it in a different color, I suppose. This is we get from this recursive call. All right, other questions? Okay. All right, so we have our guess at a closed form we just got by expanding it a few times. And now we're going to try and prove it by induction. So our base case, our recursive case, and our guess at a closed form. Our base case, so we're going to simply plug 4 into our closed form, right? So C of 4 is equal to 2 times 4 minus 4, which is equal to 4. So it's 8 minus 4. So I've shown that my closed form holds for this base case, right? So I simply plug 4 in for the ends here, and I get this. Okay. So the base case holds. Now the inductive case, or the inductive hypothesis, is I'm going to assume that this closed form is true for n minus 1. And then I'm going to use that to show that this is true. All right, so I'm going to assume that this is true. I'm going to take my recursive definition. So here I would have C n equals 2 plus C of n minus 1. My C of n minus 1, I'm going to substitute this in. 2 plus 2n minus 1 minus 4. That's equal to 2 plus 2n minus 2 minus 4. These cancel out, and that's equal to 2n minus 4. So simple. The analysis, the final analysis is pretty easy. The beauty of this is what happens in this call, I have no idea, right? It's just, it's the magic of recursion and induction. You can, of course, think about it and expand it out and solve it in a way probably iteratively, like through a for loop or something, but this is nice and elegant, solves the problem, and we can analyze it. All right. Questions? Okay. All right. Here's another quick one, just because I like this one. I don't know if you guys maybe have seen this before, but the towers of Hanoi is a problem where I have 3 pegs. Let's call them, I'm not going to go too much into detail here. It's got a neat history. The idea is that there's monks. I should really look up the history a little more, perhaps in Tibet. These monks have this towers of Hanoi problem, and they have 64 disks on one of the towers. And what they want to do is they want to move all of the disks from tower 1 to tower 3. The rules are as follows. I want to move all disks to the 3rd peg. I can never put a larger disk on a smaller disk. It'll break or something will go wrong. And I can move 1 disk at a time. Okay, so those are the rules, and using those rules, I want to get all 64 disks to the other one, and as the legend goes, once they're finished, that's the universe comes to an end. Right, so that's the Towers of Hanoi. And it's neat because how do you solve this iteratively? Well, I don't know. I could start by moving this disk here and then maybe this disk over here. So what do I have? This here and then a bigger one here. Now I can move this smaller one on top and move this next bigger one down here. I could probably come up with something. But using the power of recursion, I don't have to get into all that messy detail. I can just simply solve the base case. I can assume it's solved when I make a recursive call. And then I can, use that to solve the bigger case. So in the base case, let's say I have one disk. Simple enough. I'm going to move it from peg 1 to peg 3, and I've solved my problem. Right? So in the simplest case, I can solve it. So now the fact that I can do it in the base case, I'm going to assume that I can do it recursively. So how can I do this now? Well, if I think about what to do recursively, I can move all but the last disk to this peg, right? So I have a destination, I have a spare peg, and I have my source peg. Oops. So I can move, using the spare peg, I can move everything from disk source to disk destination, except for this last one. Right, so I can solve a smaller version of the problem. And then from here, I can do my base case. In this case, I only have my last disk to move from my source to my destination. And then now I'm going to recursively call with this as the source, this is the destination, and this is the spare. Right, so using the magic of recursion again, I simply move all of those disks to the third disk, and I'm done. Right, so I'm not going to write this algorithm out. I just think it's a nice, I used to have a bit of code I can run that would actually illustrate that, and it shows you how long it would take. But yeah, I like this example. So yeah, if I wanted to solve that recurrence, so the algorithm would go something like this. Let's call it towers. And I have my source, destination, and spare. And then let's say n disks. Okay, so I'm going to call towers. So my first, what is it? Yeah, source to spare using my destination as the middleman. I'm going to move one disk from source to destination, and then I'm going to recursively call towers again. In this case, from the spare to the destination using the source and n-1 disks. So the recursive algorithm would look something like that. And if you set it up with an animation, it looks really nice, but yeah. So we can now solve the Towers of Hanoi or count how long it would take to solve the Towers of Hanoi. Right, so we're going to count all the times that we move from one source to a destination. So if I have let's call it h of n, so h is a number of moves for Tower of Hanoi. Okay, so the base case, if I have one disk, then I do one move, right? So that is, yeah, I should have here. If n is equal to 0, simply return. Okay, so if n is equal to 1, I have one move. These return without moving anything. And now if I have n disks, well, I have again, I call h of n minus 1. That's my first call to towers, plus one move, plus h of n minus 1 again. So that's 2 plus 1. Okay. Now I'll go through this really quickly. It's sort of simple, but so I'm just going to expand it out. I have my base case. I have my recurrence. I can now plug in some values. So h of 1 I know is equal to 1. H of 2 is equal to 2 times 1 plus 1. That's 3. H of 3 is equal to 2 times H2, right? Plus 1, which is equal to 7. H of 4 is equal to 2 times 7 plus 1 is 15. So I have 1, 3, 7, 15. And if I kept going, I would have 31, 63. So my guess at a closed form would be that h of n is equal to 2 to the power n minus 1. All right. So, yeah. Questions so far? Am I losing anybody? All right. Okay, so I have a base case, I have a closed form, I have a recursive form, I have enough to solve it. So h of 1 equals 1. H of n is equal to 2 h of n minus 1 plus 1. And my closed form is 2 to the n minus 1. So I check my base case. H of 1 is equal to 2 to the 1 minus 1. That's equal to 1. So the base case holds. Now the inductive hypothesis is that h of n minus 1 is equal to 2 to the n minus 1 minus 1. So now I'm going to plug that value into here. Plus 1, it's equal to 2 times 2 to the n minus 1 plus 1, which is equal to 2 to the n plus 1. Okay, so again, very, very simple analysis. But just to sort of illustrate how we can go from solving a problem we don't really know how to solve recursively, and then we can also analyze, oh, sorry, this should be 1, eh? Yeah. This should be minus 2 plus 1. That's minus 1. So yeah, we can go from designing a solution recursively where we don't really know how to solve it. We just know how to solve it in the simplest case, and using recursion to the analysis. Yeah. Any questions on that? Yeah. Which one? This one here? Yeah, so 2 times 2 to the power n minus 1 is 2 to the power n. And then I had, so this was actually, yeah, 2 times 2 to the n minus 1, which is, yeah, so that would have given us minus 2 here. Yeah, the algebra works out. So like our recursive form here. Again, I pulled that right from the algorithm, eh? So I'm analyzing the h of n equals number of moves. So for every call, I move 1. and then I make 2 recursive calls. So this +1 here comes from this call to move. And the 2hn-1 comes from these 2 recursive calls. Yeah, so again, to make the recursive function that counts, you just basically pull it right from the algorithm. Yeah. I think the algorithms I give you on your assignment, I think I tell you what you should be counting. There's certain calls or certain operations that cost a certain amount. Yeah. In this case, I just made a guess. We're going to look at, so probably not this class, but next class, we're going to look at how to make a more educated guess. Yep. Yeah, so I guessed at this closed form. In fact, it becomes pretty obvious after a while, because if I kept going, I would simply get, I would get that number over and over again. If you do it long enough, you see these numbers long enough, you recognize them, but yeah. Yeah. Yes. In this case, we'll see when we get to merge sort, that's not always the case, right? So we can do n/2, we can do some smaller value. In the simplest case, the smaller value is n-1, but we can do fractions, we can do all kinds of things. What's that? It depends on the algorithm, right? So in this algorithm, because we specifically call it on n-1, yeah. But merge sort is something like if I have a merge sort on n, I'm going to make 2 recursive calls on n/n/2 and n/2. So we can solve that as well. It really, everything hinges on what your algorithm does, right? So I don't use n-1 by default. I use n-1 because I made calls, recursive calls on n-1 elements. All right. Other questions? Okay. How we're doing. All right. So somebody had a question. You can just write your guess. You don't have to, yeah, as long as you prove your guess is correct, that's fine. There are actually, maybe, yeah, you should show a little bit of work on how you get there in terms of either expanding it out a little bit in the values or using unfolding, which we're going to look at next class. So yeah, do show a little bit of work into terms of how you got your guess, because you can, I don't know, there's other tricks to get to the answer. So yeah, other questions? Okay. So this brings us to Euclid's algorithm. Euclid's algorithm is probably one of the oldest algorithms. So we're going to go quickly through it. Again, the part of the assignment based on Euclid's algorithm is bonus, but it is pretty neat because this guy came up with this algorithm about 300 years ago. He didn't know anything about computers, but came up with this, probably still the best algorithm for finding the greatest common divisor of 2 numbers. So what do we mean by greatest common divisor? We're going to take 2 integers, a and b, and then GCD of a and b is the largest integer that divides them both evenly, right? So with no remainder. Right, so the greatest common divisor, for example, of 75 and 45. Well, if I look at all of the common divisors, there's 1, there's 3, there's 5, and there's 15. And then the greatest of these is, of course, 15. Okay. So the greatest common divisor of a number with itself is simply the number itself. And yeah, so that's the definition of greatest common divisor. Everybody clear on that definition? Okay. So we want to find the greatest common divisor of a pair of large numbers. In this case, we could sort of, we could find we can sort of brute force it, right? So we can look at all of the common divisors and then just choose the largest one. But let's say we had huge numbers like these. How do we find the greatest common divisor? Well, there is one technique that works. I can do what's called a prime factorization. So I'm going to reduce each of these numbers to all of its prime factors, right? So 3, 5, 13, 17, and 31 are all prime numbers. That means they're only divisible by 1 in themselves. And then I can write each of these numbers as a product of primes. Okay. And then how do I find the greatest common divisor? Well, I'm going to take all of the common elements, all of the common factors from both of them. So if I can find the prime factorization, finding the greatest common divisor is easy. I have 3 squared here and 3 to the 4. Well, I have 3 squared in common. Here I have 5 to the 1 and 5 squared. Well, I have 5 to the 1 in common. 13 to the 4 and 13 to the 3. I have 13 to the 3 in common. And these have nothing in common. So once I find all the common factors, I simply multiply them out and I get the greatest common divisor. Okay, so that's one way to find it. Yeah.
So exactly did you hold like
Yeah, so that's the trick. It's very hard. Even for a computer, this is really hard. So this is, I know the prime factorization because I looked in the textbook essentially. So this is guaranteed success, but it takes a long time to compute the prime factorization. Yeah, very, very slow. And a lot of computer security is based on the fact that prime factorization is very slow. Okay, so if I have an integer with 1,000 digits, that's thousands of years to compute. Okay, so this works, but it's not the fastest. So Euclid's algorithm for greatest common divisor is sort of deceptively simple, but very, very clever. It is recursive. So yeah, we have integers a and b, and we want to find the greatest common divisor. And this is easy, fast algorithm. Oh, sorry, not 300 years ago, 300 BC. So that is 2,300 years ago. And all we need basically is the modulo operation. Okay, so similar to division, but the modulo operation is the remainder. So if I have numbers a and b, and a is greater than b, and I divide a by b, then modulo gives me the remainder of that. All right, so yeah. So if I write, for instance, if I have a mod b, then I can write a as some number times b plus the remainder, right? So for example, yeah, and in this case, q is a quotient, r is the remainder, and of course, a and b are the numbers I'm given. So if I have 17 mod 5, then I have 2 remainders. So 5 divides into 17 3 times. That gives me 15 plus 2 remainder. 17 mod 17, the remainder is 0. 17 mod 1, the remainder is 0. So 1 divides into 17 evenly, right, with no remainder. A number mod some number greater than itself is simply the number, right? So how many times does 19 go into 17? Well, it goes 0 with 17 remainder. And yeah. So I can write all these in this form. So 17 equals 3 times 5 plus 2, right? So this 5 divides into 17 3 times with 2 remainder. And I can also write out 17 divides into itself once with 0 remainder. 1 divides into 17 17 times with 0 remainder. And 19 goes into 17,0 with 17 remainder. Okay. Everybody clear on the mod function? Okay, so here is Euclid's algorithm. I take given two arguments A and B, where A is at least the size of B and B is at least 1. So A has to be greater than or equal to B. I take the remainder of A mod B, and if R is equal to 0, I return B. So in this case, I would say that B is the greatest common divisor of A and B. Or if R is greater than 1, I'm going to recursively call Euclid on B and the remainder. Okay, and it just so happens that if I divide by a number B and it doesn't go in evenly, then the remainder is going to be actually less than B. Okay. All right, so that's the algorithm. That's Euclid's algorithm. Very, very simple. Recursive. We're going to analyze it probably kind of quickly, but we'll prove that it's correct, and then we'll see how quickly it runs. So for an example, we're going to run Euclid on 75 and 45. So if I do this, yeah, I can, of course, do the prime factorization of 75 and 45. Yeah, so 75 equals 3 times 5 squared. 45 equals 3 squared times 5. So the greatest common divisor is, well, they have 3 in common and 5 in common. 3 times 5 is 15. All right. So now using Euclid's algorithm, we're going to see if we get 15. So I run R equals A mod B. So 75 mod 45. So 45 goes into 75 once. There's 30 remainder. So R is equal to 30. Since R is greater than 1 or greater than or equal to 1, I make a recursive call on B and R. So Euclid 4530. Again, I'm going to take R equal to 45 mod 30. So 30 goes into 45 once. I have 15 remainder. And then so R is greater than or equal to 1. In particular, it's not equal to 0. So I'm going to make another recursive call. Euclid 3015, R equals 30 mod 15 is equal to 0. Right? So 15 divides into 30 evenly. The remainder is 0. In this case, I return B. So I return 15. So I get the correct answer, at least in this example. All right. Is that clear? Any questions on that? All right. So we want to argue that this is true in general. So we want to argue that it's correct over all of A and B. And also we need to argue that this algorithm does indeed terminate. Right? So at some point, we're going to get a remainder of 0, and we're going to return an answer. So those are the things we have to argue. And how we're going to do it is we're going to say that this algorithm is correct if it returns the greatest common divisor of A and B, both in the base case and in the recursive case. So for us, the base case is that the remainder is equal to 0. And the recursive case is, of course, the remainder is at least 1. Okay, so we want to prove when R is equal to 0, the greatest common divisor of A and B is B. So this will prove the base case of Euclid's algorithm. Otherwise, when R is equal to 1, we have two things to prove. We want to prove that the recursive call indeed returns the greatest common divisor of B and R, and also that the greatest common divisor of B and R is equal to the greatest common divisor of A and B. So if we prove all those things, then we can say that, yes, Euclid is correct, and then we can analyze the runtime after. Okay. So we're going to start off by proving just 2b and 1. All right, and then later we will prove this by induction. So first we'll start with the math part, and the math part is that, well, if the remainder is 0, then the greatest common divisor of a and b is equal to b. That means that b divides it to a evenly. So I can write a as q times b plus r is 0, so just simply q times b. And the greatest common divisor of qb and b is, of course, b. I can't have a greater divisor of b than itself, so this stands to reason, sort of trivially true. So A is true. Part B, we want to argue that the greatest common divisor of A and B is equal to the greatest common divisor of B and R if R is not equal to 0. So if it's greater than or equal to 1. All right, so how we're going to prove that is we're going to say, well, if all of the common divisors of A and B are the same as all of the common divisors of B and R, then the greatest common divisor must also be the same. Okay, makes sense. So if they have all the same divisors in common, then the greatest one is also one they have in common. Sorry. Okay. So to prove that, we're going to show a bijection between the common divisors of A and B and the common divisors of B and R. In other words, we're going to look at just a general divisor of A and B and show that if D is a divisor of A and B, it must be a divisor of B and R. And then we're going to take our divisor D of B and R and say that, well, if it's a divisor of B and R, then it's also a divisor of A and B. And if we do that, we have a bijection, which means that the set of divisors is the exact same in both cases. All right. So yeah, questions so far? Okay, so we can write A as a product of the quotient times B plus the remainder, which means that, so I'm proving, which means that I can rewrite R as A minus QB, simply with a little bit of algebra. So that means we're assuming that A and B are both multiples of D. So D is the common divisor of A and B, which means that I can write A as D times some number A prime. I can also write B as D times some number B prime. And then I can plug these values into here. And then I can see that R is equal to dA prime minus Q times dB prime. Right? So I'm simply taking this, which I got with a little bit of algebra. I'm plugging in these values. And then dA prime minus Q, B prime D have a common factor of D. So if D is a common factor of A and B, which we assume here, then it's also a common factor of R. Okay. So we've shown one direction of our bijection. Now we have to argue the other direction. So again, we're going to use this. And again, we're going to, this time we're assuming that B and R have a common divisor D. And then we're going to show that it's also a common divisor of A. So I'm going to write B as D times B prime, which I can do because D can divide it. I'm going to write R as D times R prime, which I can do because D can divide R. Then when I express A as QB plus R, I can again take out the common factor of D. So again, if D is a factor of Q and R, it's also a factor of A. All right. Questions on that? I mean, a little fancy way to explain something simple, but all right. So we have our bijection. We have If D is a common divisor of A and B, then it's also a common divisor of B and R. And if it's a common divisor of B and R, that's also a common divisor of A and B. So they have all the common divisors are the same. So that means the greatest common divisor of A and B is equal to the greatest common divisor of B and R. Thus, we've shown that this is true. All right. Yes, this part of the lecture is a little heavy, but so yeah, lemma 1 that we wanted to show. Yeah, A and B were both true. Lemma 1 is true. So now we have this fact here that we can use in our proof. So we're going to take our Euclid algorithm and prove that it's correct using induction. Okay, so yeah, we want to show that it terminates. So we have to rank each of the calls to Euclid. We can rank it on the size of A. So if A is equal to 1, which implies that B is equal to 1, then of course this returns, it does terminate. Otherwise, yeah, all right, so we're going to do both at the same time. So assume that Euclid BR returns the greatest common divisor of B and R, as long as B is less than A. We're going to use that to prove, yeah, I think I mixed up my proofs here a little bit. All right, let me see where we're going. Okay, so we're going to skip the termination part because I don't have it here. Essentially, what happens is that every time I make a recursive call, A decreases by 1, so we know that Euclid will terminate, which is great, because once we get down to Euclid 1,1, we're guaranteed to return. So we can prove that it terminates, and now we're going to prove that it's correct, in that it correctly returns the greatest common divisor of B and R on a call to Euclid BR. Okay, so if the remainder is 0, Euclid returns B, which we've already shown is correct, right? The greatest common divisor of A and B, if there's no remainder, is B. Otherwise, we're going to make a recursive call to Euclid. This call is ranked, so we can apply induction, which means that our inductive hypothesis, we can assume that this is true. So we can assume that Euclid BR returns the greatest common divisor of B and R. And we've also shown that if R is greater than 1, greater than or equal to 1, then the greatest common divisor of A and B and R are the same. So we've shown correctness of Euclid's algorithm. Yeah, minus a little bit about determination, but yeah. All right, questions? Probably there's questions, but it is sort of heavy. So yeah, basically we did the same thing we did with the other ones, but in more steps. We had a bunch of intermediate things to prove. But yeah. Yeah, at a high level, proving that it terminates ranks all the calls to Euclid. And then because we ranked them, we could apply induction. And then we used induction to prove it's correct. Okay, so let's look at the runtime. So how efficient is a call to Euclid AB? So we'll look at this example. So yeah, we want to count the number of times this mod step is executed. So this will be our significant operation that we're going to count. And we're going to let this function MAB be the number of times this mod is executed, so the star. So if we go to look at this execution again and simply count them, well, we have one call initially. Then we make a recursive call. We have another call to mod here. We make another recursive call. We make a final call to mod here. At which point we simply return 15 So this MAB for 75 and 45 is equal to 3, right? So I made 3 calls to this mod function, which is in some sense the number of recursive calls that I make. Okay. All right. So yeah. So in the easiest case, we're going to do an easy analysis, then a harder analysis. So the easy analysis is that the number of times this line is executed is at most B. So my second argument here, I cannot make more recursive calls than B because, well, B is always at least 1 and B always decreases by at least 1. So every time I make a recursive call to Euclid, I replace B with the remainder. Of course, the remainder has to be less than B by definition. If it was equal to B, then the remainder would be 0. So yeah, the number of recursive calls we can make is at most B by our easy analysis. But we can do a better analysis based on the Fibonacci sequence. And we can do that. First, we'll look at sort of the idea behind it, and then we'll go through the math, and then that should take us pretty close to the end. So if I look at the sequence of calls to Euclid that are made, so I have 75, 45 here, and then I have 45 and 30 here, and I have 30 and 15 here. And if I write all those in sequence and get rid of the repeats, maybe you notice something about this. For instance, 45 is equal to 30 plus 15. And also that 75 is equal to 45 plus 30. So if we look at the numbers in sequence backwards, then we have, it looks sort of like a Fibonacci sequence. Maybe not exactly the Fibonacci sequence, but with a different base case, then it kind of looks like the Fibonacci sequence. So that's what we're going to base our analysis on, is this fact that, yeah. All right. So we want to prove this lemma. We want to show that the number of recursive calls M, A, B, for A and B greater than or equal to 1. If M is the value or the number of recursive calls we make, then A, the size of it is at least the M plus second Fibonacci number, and the size of B is at least the M plus first Fibonacci number. So that's our claim. So if we make M recursive calls to Euclid, then these numbers are the size of roughly the M, M plus second and M plus first. Yeah. So we're going to, does that mean M is large or small? Well, we're going to answer that in a second. So the idea behind the proof is that we have A is equal to some number Q times B plus R, which means that A is at least B plus R, right? So we have that sort of a Fibonacci feel to it, or the idea behind it. Okay. So we have, yeah, Fn equals f of n minus 1 plus f of n minus 2. And A is similar, but it's perhaps even bigger because Q might be greater than 1. So yeah, it sort of looks like the Fibonacci sequence if we write them out like this. So this means if this is true, which it is, then if R is at least the f of n minus 2 Fibonacci number, and B is at least the n minus 1 Fibonacci number, then A must be at least f of n. All right, so we're going to prove all of this and yeah, use that to bound the runtime. Okay, so we want to prove this lemma that A and B are at least these Fibonacci numbers. our base case is m is equal to 1. So we have no recursive call. We make one call to the mod function. So we have, yeah, we could say that if m is equal to 1, we make one recursive call that's equal to the first Fibonacci number. So now we'll look at if m is greater. Yeah, and since b is at least 1, which is f of 2, and a is a little bit greater than b, otherwise we would have returned right away. Is equal to f of 3. So yeah, we have a Fibonacci sequence f3 equals f2 plus f1. So yeah, our base case is true. So our inductive step for m greater than or equal to 2 is, yeah. So if I'm going to make one call to my mod function here, and then I'm going to make m minus 1 recursive calls in total on this recursive call, right? So m is by definition the number of recursive, or the number of calls I make to Euclid. All right. Yeah, so by induction, I get these two things are true, right? So my inductive hypothesis, this is what I'm trying to prove. So my inductive hypothesis gives me that b is at least f of m plus 1, and r is at least f of m. And then, well, at this point, I can write as a as the sum of q times b plus r, which is at least f of m plus 1 plus f of m. So a is at least f of m plus 2. So our inductive hypothesis gave us this on a subsequent call to Euclid, and that proved this directly. And then using this function, I proved this. So then I've proven the whole thing by induction. All right. So the entire idea behind it, I know this is a very mathy lesson. The whole idea hinges on this. When I make a recursive call, I do it on b and r, and a is at least b plus r. So it has that Fibonacci sequence to the subsequent calls. And once it gets to 1, then it's going to end no matter what. So yeah. All right. Questions on that? Yeah, it's a heavy lesson. So that's why it's a bonus question. Okay, so if you can sort of map the question 9, I think it is, to this Euclid's algorithm and sort of figure it out, it's not, I don't think it's as hard as it looks. Proving it is, of course, a little bit, I don't know, nightmarish, yeah. That's appropriate, yes. Yeah, proving it is a little sticky, right? And it's, yeah, anyway. All right. So now we know that lemma 2 is true. So, and we know that we're going to use that to prove lemma 3 here, which is that the number of recursive calls MAB is at most 1 plus log of, and I use the wrong Greek letter here, but we'll call this phi 1 plus root 5 over 2. So this number is one of the roots of x squared equals x plus 1, and it's part of the closed form of the Fibonacci sequence. So we're going to use that. Yeah, so it's about 1.6. So Euclid's algorithm runs in about log of n time, right? So that's the claim. Yeah, so if a is equal to b, then m of a and b is 1, right? We only make a single call to this mod function. This 1 is less than 1 plus log of phi of b. And if a is greater than b, then m of ab is equal to m. So I have b is at least the f of m plus first Fibonacci number. which is at least phi raised to the m minus 1. So we're not going to do that here. Yeah.
So it's fine.
Yes. This is one of the, when we proved the closed form of the Fibonacci sequence, we used this. It was actually, it's supposed to be this. I wrote the wrong Greek letter, but yeah, it is a constant. It's one of the roots of this quadratic equation. So one of the values of x that make this true. All right. So I'm going to give this to you without proof. I think we've seen enough math for one day. But yeah, the m plus first Fibonacci number is at least phi raised to the m minus 1. And we know that this is true because we proved it. So if we take the log of both sides, base phi, we get log base phi of b is at least m minus 1. So m is at most 1 plus log phi of b. Right? So it's a fast algorithm. It's as fast as, let's say, binary search. Depending on how you define input size, of course, but yeah. All right. Questions on that? Yeah. This Euclid's prime factorization is very slow. Yeah, so that is the alternate way to prove or to find the greatest common divisor of two numbers. Euclid's algorithm is actually quite fast. All right. Yeah. Questions? Yeah.
Simplest way to think about Euclid's algorithm, like which lemma?
The simplest lemma to prove, or the most necessary?
I guess.
Let's take a look. So you're thinking of working through it. I would, there's some nasty stuff in here. I would work on maybe trying to prove that Euclid is correct. And I think you could do it. I think my thing crashed. I think you could do it without too much difficulty if you took some liberties and weren't super rigorous, right? Because I'm not going to ask you anything this hard. So even if you can sort of convince yourself that it's true, that's progress. Yeah, I mean, you have to kind of do all the painstaking detail, but you know, like if we were talking about this on the board and discussing it, I would really gloss over a lot of this stuff because the ideas are the important part. And the idea is that, I'm pretty sure my computer crashed, but the idea is that I can prove this recursively, like the recursive call to Euclid, the same way as we did the other ones, right? Those were very, very simple. And this is very, very complex, but in principle, it's all the same. There's not a lot different going on. Other than this, you have to prove it terminates, but if you assume it terminates, then the proof gets way simpler. All right, yeah. Other questions? Okay, we got 5 minutes left. I have to see if I can, I don't know what the hell. What's that? Yeah, I wouldn't ask this on the test. I mean, I did it as it's part of the textbook, and it's a cool kind of proof, but it is really heavy. I wouldn't on a test. This would be too long. If I ever had written tests, then yeah, I could do that. But all right, we got 5 minutes left. Let's maybe look at something a little bit lighter, a little bit easier. So this is closer to what I would ask you on a test, right? So Fibonacci sequence comes up a lot. And the number of 0, free bit strings comes up a lot because we can relate it directly to the Fibonacci sequence. So it's kind of nice. And there's lots, you can recursively define this a lot of different ways. So in this case, we know that the number of 0, free bit strings of length m is equal to f of m plus 2. So we're going to call that, what did we call it? B of m equals f of m plus 2. B of m is 00 free bit strings of length m. Okay. So yeah, so we're going to take 00 free bit strings of length 2n minus 1, and we're going to assume that the bit in the middle position is equal to 1, and we're going to count those. Okay, so we have some bit string that's 00 free, and the middle is, what would that be? 2n minus 2n minus 1, so this would be position n. And we assume that's a 1, and this would be n minus 1, and this would be 1. And then this would be up to 2n minus 1. So this is a 00 free bit string, and I'm telling you that, or I want you to count the number of 00 free bit strings in which the middle bit is a 1. Okay, so this is similar to how we count them in general, right? We say, well, if we fix it to be a 1, is there any restriction on any of the other bits? Well, all we really need is that this is 00 free, and this happens to have a length of n, right? So the number of 00 free bit strings of length n is, well, f of n plus, did I do that wrong? 2n minus 1. Sorry, this is length n minus 1. So this is f of n plus 1. So the number of 00 free bit strings that I can put there is equal to the n plus first Fibonacci number, right? Because this has n minus 1 locations, and this one also has n minus 1 locations. And again, I have no restriction. So this is also equal to the n plus first Fibonacci number. So the number of 00 free bit strings of length 2n minus 1 in total is, with 1 in the middle, is f of n plus 1. So I choose this bit string, then I choose this bit string, right? So that is a sequence of tasks. So I use the product rule. So f of n plus 1 squared, right? And you can get a hint from the answer here. The next question is, well, what if the middle position, the bit in the middle position is equal to 0? Okay, I can do the same thing here. I put a 0. If I have a 0 and it's 00 free, then I also know these two bits. Neither one can be a 0, right? Which means that now this is, if I look at the length of this, it's now n minus 2. And the length of this is also n minus 2. So now the size of this is the nth Fibonacci number. The number of possibilities here is the nth Fibonacci number. Again, this is a sequence of tasks. So I use the product rule. First, I choose a bit string, a 00 free bit string of length n minus 2 here, and then I choose another one here. So this is f of n squared. Right? Well, if I add all of the bit strings with a 1 in the middle and a 0 in the middle, they're all 00 free. Well, that is all of the bit strings of length 2n plus 1. Of length 2n minus 1, which is the 2n plus first Fibonacci number. So that's how I get this, is the sum rule. So f of 2n plus 1, which is the number of 00 free bit strings of length 2n minus 1, is equal to f of n plus 1 squared plus f of n squared. Okay, so questions like that you would absolutely are fair game on a test. They're short, they're easy, but you still have to sort of have knowledge of how these recursive things work. All right, that's it for today. I will see you guys on Thursday.